like to introduce Professor Cath Noakes from the University of Leeds. Over to you, Cath.
Thank you for inviting me to come and talk at this meeting. Marcella asked me to come and talk a bit about what we know about COVID-19 and what that might mean in terms of its transmission, its survival, and some of the things around air quality, well, some of the implications for the indoor environment. So what we know about it, we know it's a very small virus. It's about 100 nanometers. It's an envelope virus. It has a lipid bilayer. It actually means you can wash it off your hands with soap very easily. We think it is dispersed predominantly through respiratory aerosols. I say we think, there's no absolute proof of that. It's just that is where the international consensus is. There's also a possibility that it may be released through fecal aerosols. There has been some evidence that it's in feces, so that could be released from sanitation systems in buildings. Although whether that's a risk or not, is hard to say. And the evidence so far seems that transmission is likely dominated by short range transmission, so predominantly close contact, prolonged contact. That might be contacting surfaces, it might be that you're at very close range with somebody, so you inhale the droplets that they produce and at a very short distance. And prolonged exposure seems to be part of that. So there's growing evidence that the majority of the transmission is in indoor environments. There's very little transmission happening outdoors that can be identified. And there's, although it's not considered to be widely as an airborne disease, there is some growing evidence that there is airborne transmission that could be happening in poorly ventilated spaces. So it's likely most of it's droplets and contact, but there could be some aerosol transmission in certain spaces. And I guess that follows many respiratory pathogens in that it's released through a cough or a sneeze, in a big distribution of droplets that may range from 1 to 100 microns. Those droplets will evaporate slightly. They'll be transported through the air depending on how they were ejected, depending on their size. They'll deposit onto surfaces. They may deposit directly onto somebody's face and therefore transmit through the nasal mucous membranes through the eyes. They may be inhaled and deposit in the upper respiratory tract, and the very small ones potentially could get inhaled and get deposited down deeper in the lung. And we don't know the relative importance of all of those factors at the moment. I think the whole process is likely to be very complicated. I mean, for any of these sort of respiratory pathogens, it's a very complex relationship between the physics and the biology and the people. There's quite a lot of papers and things that are appearing on the internet about cough particles, where do cough particles go. I think something that's important there is remembering that not all cough particles carry a virus, and just because somebody is producing cough particles that is, a lot of very small particles, doesn't mean they're all carrying virus. Actually sampling for microorganisms within a cough is very hard. There are very few studies that have done this for any diseases, let alone this one. And so to understand exactly how many microorganisms or how many virus particles somebody produces is quite difficult. It's quite likely that will depend on the viral titer, whether it's related to what's in somebody's throat, nose or saliva, we don't know that yet. But we do know from papers that have been published so far that the viral titer amongst people with COVID-19 varies hugely, so it can range from sort of 600 virus particles per mil up to 10 to the 11 virus particles per mil. It's a huge range. The majority seem to be somewhere around 10 to the 6, but that's hard to say it's going to be the case all the time. Something that's quite important is that it won't be released as a naked virus. So as it's released as a cough aerosol, it's released in respiratory droplets, and those droplets are not water droplets. They contain proteins, surfactants, salts. I'm sure somebody in the more medical people in the audience will know many other things that are in there, but as they evaporate, those things remain, and many of those other substances are bigger than the virus itself. So we won't get 1 nanometer virus particles floating around on their own. They will be with other things predominantly in the environment.
One remarks, please.
Sorry?
You got literally 1 minute.
1 minute. Oh, better go faster then. So we know that shedding may depend on the individual, the different stages of infection. Where those droplets go is incredibly complex. It's going to depend on the particular environment, the interaction between the human and the space that they're in, and the ventilation patterns. We know the virus is stable in aerosol. In laboratory conditions, it says 3 hours or more. Deposition on surfaces and surface contamination is probably very important, and we know that it can survive on surfaces for a long time. Some of it's about 4 hours on copper, but 2 days on plastic and steel. There's data showing that at 4 degrees C, so possibly chilled environments, it can stable for 14 days. It doesn't like heat and humidity though, so it will die more frequently there. Also, there is some evidence that it dies very quickly in bright sunlight outdoors, so there's a suggestion only a few minutes outdoors. Just to touch on where the research is going with this, I think there's a focus on how to control it, and the controls need to think about the 3 different routes. So contact transmission is all around hand hygiene, surface cleaning, no touch surfaces, touching your face, etc. Droplets and short range transmission, things about using face coverings as a source control, but staying that 2 meter distance, avoiding face-to-face contact, using things like screens to protect people. And then the airborne transmission, ventilation and use of UV light, air cleaning devices are all part of that. And then for all the transmission routes, there are some issues around how do you, if you can reduce the occupancy, you reduce the viral load in a space and reduce the chances of coming in contact with an infectious person. And if you can reduce the time of which people are exposed, like for example changing shift patterns, then you might stay below the infectious dose. I just wanted to finish up with a couple of things around research questions, because some of you are aware I'm on the SAGE committee, so therefore some of these things have come out of what the discussions we've been having. There are some very big questions around transmission, so we don't know much yet about we don't know how much dose you have to get to be infected, but it is very important. Just because there's a droplet in the air doesn't mean there's enough to get infected, and that's really quite important to remember. We don't know much about the prevalence of the virus in real environments. There is some sampling from hospitals, but we don't actually know what prevalence is in a school, the London Underground, a bus, or any of those sort of environments. We don't know that much about how people shed the virus and where they're shedding it and the amount they're shedding at different times in their disease. There's a lot of questions around the biological and physics of the droplet behaviour. We don't know the relative importance of the different transmission routes, and we don't know much yet about the importance of fecal shedding. So there's a lot of very big research questions on transmission. Possibly more related to this group are the research questions around the environment. So how might we mitigate transmission in different environments, and very specific environments like places like schools, care homes, hospitals, close contact occupations, so that ranges from dentists through to hairdressers, and transport environments. So all of those have very specific challenges which are difficult. Thinking about different mitigation measures, what are the synergistic effects of those? You know, a lot of people are focusing on what do you do with a mask, or what do you do with hand washing, but actually how do these things all interact together? If you do one thing, does it affect another thing? I think there's some much bigger longer term questions which are more geared towards the longer term research about how do we adapt our buildings to now become more resilient? How do we now balance the energy and comfort challenges with dealing with risk? How does human behaviour interface with that? So whether it's an engineering challenge or a human behaviour challenge or both. How do we adapt our different behaviours but don't lose the social context in which we're doing it? And a really big one that's going to hit us all is what do we do in winter? Because the summer's quite easy, or relatively easy. We can do a lot of outdoor stuff. We can socially distance more readily. We can ventilate our buildings better. What do you do in the winter? Final thing I just wanted to mention.
Final words.
This is a very final one. These are big interdisciplinary questions. They're not easy to answer in small projects, so a lot of them will need to engage in bigger groups across discipline, which is really important. It's worth noting for the rapid call, there is a question in there that says, will a research have an impact on public health within 12 months, and how are you going to show that? So bear in mind that if you're thinking about applying for that rapid call.